And just hide this. No. And over here. Okay. It's video page. And this floating window. And I think is this. Just to remove this part. I don't know how to do it. I think there is something called hide video floating. It's gone. Okay. Can I move it to the left? Yeah. Go to the right? Yes. Sure.
Hello, everyone. Welcome to another Safari Live seminar. Today is my great pleasure to introduce you Professor Jihong Kim. He's a professor in the Department of Computer Science and Engineering in Seoul National University. Before joining Seoul National University, he was a member of technical staff in the DSPS R&D Center of Texas Instruments in Dallas, Texas. Jihong Kim received his Bachelor in Computer Science and Statistics from Seoul National University and Master and PhD degrees in Computer Science and Engineering from the University of Washington. His research interests include NAND flash memory storage system, low power systems, computer architecture, and mobile computing. So,
thank you.
Thanks a lot.
Thank you for kind introduction, Mohammed. It's my pleasure to be here this morning. So it's a little probably busy time other than the academic reasons, but it's my pleasure to be here to share some of my research experience on SSD. And so what I'm focusing on this morning is I will focus on some of my group's research work on 3D flash memory. And especially we thought about these ideas for a long time when the industry switched from 2D flash memory to 3D flash memory. And so in order to understand what is the key research directions when we make this kind of transition, and we did some characterization and observations. So I'm going to share some of our findings in this direction. So in terms of cross-layer asset optimization for 3D flash memory characteristics. Okay, before I present today's topic, let me briefly give you some of the overview of my SS research group at SNU. So my group actually exclusively focus on NAND flash-based research, and so we are looking at all the layers in terms of SSD development, starting from NAND flash memory to controller and firmware. So this is more like a storage device side, and then we are also looking at issues from the host side that interacted with the SSD I/O optimizations. So we are looking at reliability issues and performance optimization, also lifetime extension, and also we are looking at some special functions we can add on to the SSD. And so some of very difficult, challenging problems can be more easily solved. And currently, we are focusing on more on security aspect, like ransomware protection or data sanitization kind of thing. And so these topics, most of them I'm not going to present, but if you are interested, I can open to further discussions after the seminar. Okay, so let's go back to today's topic. So it's mainly on 3D flash memory. It's a starting point. As you're very familiar with already, the 2D flash, when it reached its capacity limitation, we switched to the 3D flash memory. So 3D flash memory enabled continuous storage growth, so we can put more data into smaller device. So when we made transition between 2D flash to 3D flash, so my group looked into some basic questions in these changes. What will be the most important change that will affect SSD performance? So obvious change is 2D to 3D. Now we have a different organization because 2D is planar and 3D is cubic. In addition to that, and we wanted to understand there are any significant characteristic changes so that we can utilize in optimizing 3D pressure-based storage systems. So what we did was we look at the key changes, and then we started from there, and we did some characterization study of flash memory, and then we observed some key findings, and then we applied those findings to optimize SSD performance. So obviously, organization has changed. In 2D flash is more planar, and so here each block consists of multiple word lines in the 2D plane. In 3D flash memory, and you can consider the easiest way. I tried to understand this myself also. At the beginning, I had a very difficult time to understand, but the easiest way to view 3D flash memory is you can think a 2D planar flash block was rotated upward. So this one block became one vertical block. So in this presentation, I'll call it vertical layer. And then we added more vertical layer. So this becomes 3D flash block. So one word line here mapped to one word line here, but here now we have a cubic positions. So you may think this organization changes will give us some characterization changes, because now in 2D flash, you can consider only where in the 2D XY position, but now we have XYZ position. So depending on position, if there is some changes or differences, we may take advantage of that. Okay. So organization changes one big change in 3D flash memory. Also, so in this talk, I'll call this layer is a vertical layer or V layer. So there is a 4V layer, and then on the horizontal direction, we call H layer. So here, there are 4 H layers too. Okay. And also in 3D flash, changes in manufacturing process and material changes, and there's a big reliability characteristic changes. So when you manufacture 3D flash memory, you stack place cells and then make a big hole. And making hole with uniform diameter is very difficult. So depending on where your H layer position, for example, this one is a little exaggerated, but at the top level, it has a bigger radius, and bottom level H layer, it has a smaller diameters. Because these changes give you reliability changes. So depending on geometric position, place cell has different characteristics. Also, in 3D flash memory, there are new reliability problems emerging. For example, early charge loss is a representative problem. So there are reliability-wise big changes, and so we want to understand how these changes will affect SSD optimizations. So what we focused was, because even in 2D, people knew there is a big process variabilities among different pressure word lines, but we wanted to confirm this process of variability aspect of 3D flash memory. So we did some characterization study using in-house test board and real place chips. So something like this one, commonly used in industry to evaluate characteristic of reliability. Using 48 layer, so it is the early version of 3D flash memory. So 48 layer 3D flash chips, you used 160 chips, and out of 160 chips, we picked randomly 128 blocks per chip. So this is also kind of standard procedure for evaluating the flash memory characteristics. So through this characteristic study, we observed process variability. So in terms of process variability, let me give you a simple definition first. So when we consider 3D flash block, we consider two variabilities. because now we have two different directions. And vertical direction, we call delta V, and horizontal direction, we call delta H. So given one layer, for example, one horizontal layer here, delta H is defined as a ratio between worst word line versus best word line. So here, what metric I want to use doesn't matter. So delta V we define as ratio between worst and the best word line in vertical layer. So in these three word line, worst and best, and delta H, we look at the horizontal variabilities. So delta V, delta H, for example, in this case, delta H becomes 132. So best is 1, or best is the higher the better. Lower the better. Actually, the worst is 3, and best is 1. So delta H becomes 3, and delta V becomes 6. So we will use this abstract level of delta V and delta H as our process variability metrics. But what we actually used was when we evaluate the flash reliability, we typically goes through something called program erase cycle. We write and then erase, write, erase, because this wears flash cells out. So we use this sequence of program erase as a program erase cycle, or in short, we call PE cycles. And after XPE cycles, we spend T months time. So we call this a retention time. So just putting data there, and then we calculate number of bit errors. We denote as NXT. So this is a typical metric when we evaluate flash cells wear status. So we compared this best and worst metrics. For example, in specific case, delta V, delta H, we used delta V given vertical layer, we chose maximum NXT. So XP cycle and then T retention time versus minimum NXT. And delta H for the same horizontal layer, we computed the ratio between max and min. And then this defines the process variability we are interested process similarities. So when, for example, delta V is similar to 1, that means worst and best word line has almost same characteristic, at least this metric, in this case, NXT. So that means process variability doesn't exist. Or delta V becomes very large, there is a severe process variability. Okay. So we evaluated 160 nanoplate chips, and what we observed was similar to 2D flash. 3D flash also has process variabilities. However, the degree of process variability is much higher because the blocks are, as explained to you, different positions, geometry, and also block becomes much bigger. It has more word lines. So it's a severe process variability. But one surprise was we also found in 3D flash memory, there is a strong process similarities. And process similarity it didn't exist in 2D flash memory. But in 3D flash, we observed process similarity between horizontal layers. So what we did was, based on this observation from our characterization study, what we did was we developed a sequence of optimization techniques, and those are main topics of my presentation this morning. So let me start with the process similarity, because this one was new and it didn't exist in 2D flash. So we exploited the process similarity for improving read and write performance of 3D flash-based SSDs. Okay, so what I mean by process similarity here is going back to delta V and delta H. And so on the graph on right-hand side shows there are 4 word lines, and then each word line we measured delta V and delta H. Okay, for example, word line 1, we measured delta V and delta H in this vertical layer. So within same vertical layer, we assumed that there are 4 word lines, and each word line we measured delta V and delta H. on this layer. And if you look at here, delta V turn out to be 1.6. That means best and worst word line, there is a 1.6 difference in terms of number of errors. Similarly, word line 2, word line 3, word line 4, we did the same experiments. But if you look at this horizontal direction, so if you look at this here in picture, this green, blue, or red, within same horizontal layer, what we observe is process similarity. So delta H, very close to 1, all 3. Okay. So we repeated these experiments varying number of P cycles and amount of retention. So we simulated like fresh SSD and old SSD and young SSD, and we got the consistent result. For example, in this case, represent old SSD after 2K P cycles, and we put data in 1 year retention, and what we measured was similar. All 3 horizontal layer have a almost same NXT. So this similarity gives you very strong motivation for read or write optimization. So idea is very simple because, for example, here we have 4 word lines on 1 H layer because their characteristic is virtually the same. So what it means is if we know characteristic of 1 out of these 4 word lines, we can reuse for the rest of word lines. Because inside the SSD, there are many parameters are collected, and we flash controller optimize which level to read, how to write data, and there are many optimization going on. And in that process, this can be used very effectively. Okay. So for example, this is overall idea. So because of there are strong process similarity, what we can do is, for example, this is particular layer, 1 horizontal layer, we pick 1 word line. Okay? It doesn't matter in this position. Any one of these 4 word lines we can choose, and we understand their parameters, and then based on these parameters, we optimize their operation. So once we compute this optimization based on reading word lines parameters, then we can reuse those optimized setting for the remaining word lines. So when we optimize another horizontal word line, as long as we have 1 word line, here we call reading word lines parameters, we can apply same optimization to the rest of same word lines in the same horizontal layer. So that's the key idea of this process similarities. Okay. Yeah.
Could you please tell about the parameters? What kind of parameters are collecting and optimizing it?
So when you, for example, when we do read operation, so we have to set particularly the reference voltage, which give you the best probability of correct flash data. So you have to choose the read voltage, for example. And also when you write data, and so I didn't introduce you the basics of flash memory, but the flash cells maintain different states by different voltage level. So when you write particular level, you have put the particular voltage level to that state, that cell. And so you repeat program, adding small voltage incrementally. And so depending on how many times you go through this repeat process, it determines your program or write latency. So if you know in advance, for example, you can go, you need only 5 steps, and remaining word lines, you don't need to go that process again. You can just pick the 5 as the answer and you apply. So that's the idea. Mm-hmm. So any other questions? Yeah. No? Okay, so we apply this idea. So this is summary of our the techniques. And for example, program latency, we can improve up to 35.9%. So also read latency, we can improve up to 66%. So this is a simple idea, but previously we didn't explore it because process similarity, we didn't fully understand. And so this process similarity comes mainly from manufacturing characteristics, because as you stack up press cells vertically, each layer becomes similar characteristic, but as you go up, it's different characteristic because making a hole inside give you like geometric changes. Okay. So let me give you program side only, because read latency is a little simpler, although it gives you much higher improvement. So let me give you some examples how improved program latency here. So as I briefly mentioned, let me explain how NAND flash program operation is performed. When we program or when you write a particular state to the press cell, our physical goal is to set the threshold voltage of the press cell to the specific value. Okay, so we do that process by using program pulse and just adding a little bit of voltage, and then there's something called verify pulse. Then we check whether the current cell, the voltage reached our target. If it didn't reach our target, and we do another program and pulse, verify pulse, and we keep this step n times. So this define the program latency. And so as long as you can reduce number of steps, or if you can skip some of the program pulse or verify pulse, you can make your program latency shorter. So it give you higher performance. Okay, so I'll use process similarity in achieving smaller read latency. Okay, so left-hand side, this picture shows the default program pulse and verify pulse sequence. And let's assume it required 5 steps. And if we have this information, okay, from reading word line, and now we don't go over all 5 steps at the same time. Remaining word line, we may skip. For example, here, verify pulse, because we know after step 1, verify will fail. And after step 2, same. So only we verify step 4 or step 5. And this gives you, for example, about 16% improvement in terms of program latency. So you can apply similar ideas here and there. For example, here, we can reduce program steps. Here we use the 5 program steps, but if we knew 5 steps are answered, then we may skip some of them. So here we use only 3. So it can improve like 19%. Or if you apply this more like Birdstyle versus regular IO kind of optimization. So if you want to make your workload as a Birdstyle and you want to make a best performance on Birdstyle request or burst write request, what you can do is, so now we have traditionally we program each presenter at a time. So request comes in, then we write 1, 2, 3. So 3 different H layers are programmed. But now we can change this program sequence depending on write workload. So for example, if we can do reading word line first somehow, then what we can expect was remaining 9 word lines here can be used very fast in terms of writing speed, because they all know reading word lines parameters. Now it doesn't take long. So this kind of scenarios are possible. For example, if we know burst rise comes in sooner or later, and then now it's not that stage, then we can use, when the write request comes in, we can program only reading word line, and it'll take some time. It's slow, but now, as long as we finish one reading word line, we reserve 3 fast word lines, and so these 3 fast word lines can be used first-wise in the future. So this is another extension we can consider. So using this one, we can do FTL level. So based on this characteristic, we can do FTL level dynamic order allocations. Depending on host-wise comes in, for example, simple implementation might be we have a write buffer in SSD, and write comes in not intensively, but there is some threshold, and write buffer threshold is below, the current amount is below the threshold, then we can only use slow word line. And when the write comes in intensive way, and then we use fast word lines, we reserve the already. Okay, so simple heuristic. So based on this one, we compared with existing approaches, and then what we can observe was we can do about 48% over conventional SSD, FTL, IOPS performance-wise, and then in terms of another the test case, IOPS is improved about 3.7 times. And here, in this particular case, like 3.7 times, most of optimization comes from actually read optimizations. Even though I didn't present, we apply the same idea of setting the read level, and we can achieve almost 3.7 times. Okay, so any questions? I just gave you an overview of our approach, and if you have any specific question, I can explain more. Mm-hmm. Yeah.
Yeah, I have a couple of questions.
Sure.
So first, so regarding that experiment that you calculated in XT, so should we wait for 1 year for the experiment, or is there a way to accelerate that retention time?
Oh, sure. We didn't spend 1 year.
Yeah.
It's impossible. Yeah, usually we use oven to increase temperature. It accelerates. Yeah. Mm-hmm.
And so for the read performance, the reason, I mean, it comes from the reducing the number of read retry, right? Is that the only reason that we are improving read performance?
Yeah, in this paper, I think the read retry optimization is main. Yeah, because when you assign the reference voltage, and this process was quickly done. Yes.
And do you have a number that's how much you reduce read retry operations?
I don't remember.
Okay. Okay, and yeah, I have one more, but do you have some?
I had.
Yeah.
So can this process similarity be also exploited to optimize arrays operations?
Arrays operation? No, we didn't look at arrays. Do you have any idea?
I was thinking that I mean, similar to program and arrays also has a verify process, I suppose.
Yeah.
Maybe that.
But I think that the reason we didn't look at arrays is because read and program, it directly affects IO performance, but arrays is a little bit difficult to connect.
Exactly.
Yeah, because it can be postponed.
And it happens at the block level, and I guess similarity is between pages now.
Exactly. Yeah, that's true. Yeah, that's another point. Yeah, similarity is even horizontal layer. So one part of big block.
And also this, when you look at the process similarity in the block, did you find any patterns in terms of which word lines have the same kind of, I mean, are these edge word lines which have which are more weak, or some word lines in the block which are more stronger for error?
So that's a process variability aspect. I'll explain. Yeah, okay. But here process similarities, you have multiple word lines within same block, and depending on horizontal layer, doesn't matter where, vertically, and it has the same characteristic. Yeah. But among them, there is a big process variability. Yeah. Okay.
So one more question we have. So based on the similarity, so you are kind of making a prediction that's
Sure. Yeah.
So is there a case that we mispredict also? And if so, what is the
Penalty?
How should we handle it?
Okay, that's a good question. I think we mentioned in the paper. So in the reader, when you predict read voltage, and you will suffer, but it doesn't happen. Like very rarely happen. That's our key observation. Yeah. So process similarity is almost delta H is almost 1.
I see.
So exceptional cases very few. Yeah. When you program, I think for example, originally you predicted it will take 5 steps, and then you just follow the 5 steps, and then it might be already programmed there. So you might have overprogrammed. So in order to save that kind of overprogram case, we actually I didn't show you detail here, but when we did skipping program step, we actually stopped instead of here.
Yeah.
We conservatively we followed 3. Yeah. So this kind of take care your concern. Yeah. Good question. Yeah.
There is also one question in YouTube. How was this optimization not exploitable in 2D flashes?
2D, you don't have a horizontal similarity because the horizontal layer, the similarity mainly comes from manufacturing characteristic. So 2D doesn't exist.
Are there any questions from the Zoom audience?
Yeah, I have a question also. So regarding similarity, so did you study how similarity changes with the newest generations of 3D NAND flashes? So is it something that has been constant throughout the vertical scaling as well?
We haven't tried the very recent as NAND flash memory, so I can't say for sure. But unless the manufacturing process will change, I think it will maintained. But
Because
I haven't verified. You haven't verified. It's not easy to verify. I'm not in the industry, so.
Because I understand that there are 2 types of scaling, no, in 3D NAND flashes, the vertical one, and then within one layer, they may also reduce the feature size.
Yeah.
So if they do reduce feature size within the layer, then maybe similarity will become an issue, no? Like you will have less.
Could
Right?
be. Yeah. Good point. Yeah.
Okay, thank you.
Okay. Okay. Any more question?
I can ask one. You provide great reduction in latency, and it sounds really good. So my question is, like, internally we have a lot of parallelism inside these devices, and I'm not sure about the real numbers, but when you reduce latency beyond some point, I think it should already saturate the I/O bandwidth you have because of the parallelism, and I guess the benefits will reduce after some point, right? So
yeah, that's true.
Is like how much headroom for improvement after this work you have by reducing latency?
Oh, it's a difficult question. I mean, you need a lot of assumptions to answer the question because the SSD, the way SSD achieve high performance is, as you mentioned, parallelism. Yeah. Very slow read and write. We overcome by processing multiple requests at the same time. And at the same time, there is a bandwidth limitation between host and the flash channel. They are all related. And if you ask that questions, or if you give that kind of review on my paper submission, it's really difficult. Yeah. The answer, typical answer is, it's a good question. Yeah. So they're all related, but here we assume there is no constraint on bandwidth, host bandwidth, no saturation, and channel bandwidth, no saturation. So we look at the very low level NAND flash memory. What can you do? Yeah, but at least single flash chip, and this makes sense. And combining multiple chips, how you put into parallel systems is another big question.
Yeah, definitely.
Yeah. So it may or may not useful. Yeah. Because yeah. Okay.
I have another question, like regarding like word leveling. So, is there any new consideration that you need to have at word leveling in order to preserve similarity throughout the lifetime of the NAND flash?
I didn't follow your question. First, what was word leveling?
Yeah, word leveling.
Word leveling. Oh, I see. So the similarity, cross-similarity, at least from our experiments, is very well observed. I think I included that here. Okay. So in this graph, if you look at here, this is 2kp means almost end of SSD lifetime, and after 1 year retention, this is the most difficult requirement. And you can see the same horizontal layer.
Yes.
Cross-similarity is very strong still at this stage.
And,
So but yeah, go ahead.
Yeah, my question is like the word leveling algorithm. It is actually unmodified. It is the same as you would have in a 2D or like standard 3D.
So depending on word leveling, so if you look at the word leveling in terms of within same horizontal layer, it will change. But here we didn't assume that. So you understand what I'm saying?
Yes.
Yeah.
Thank you.
Yeah. The problem is when you erase whole block, okay, it doesn't really matter in some sense, because word leveling happens how you place your data and then how you erase. So this won't affect much. Okay.
Yeah. Thank you.
Okay. Any? Okay. Let me go to next topic. Okay. Second one is about process variability, because process variability has been there for a long time, and okay. So here we used process variability. So we wanted to extend the SSD lifetime. And the better way of extending SSD lifetime, we propose something called guarded delays. So here, let me focus on key ideas too here. Okay, so now topic is about the process variability. And this shows one block, okay? And within one block, and so here, how many word lines, for example, let's say there are 64 word lines, for example. And among these word lines, we counted maximum number of process erase cycles, and so that corresponding word line can still reliably store data. So this is a lifetime of word line. So if you look at each word line, there is a huge difference between the best word line, and so this is in vertical layer, and if you look at the position-wise around here, this is the best word line. It can go over up to 12K program erase cycles. And one nearby edge here, so edges are quite bad, as you can see here, and also here. But the worst in this case is somewhere in the top edges. And this one only experience up to 6.5K times of program erase cycles, and then it cannot reliably store data anymore. So there is huge variations within single block, okay? But in SS industry, from the 2D SSD, the basic assumption on the block failure or word line failure is each word line go over similar aging process, and then post word line becomes unreliable, and we assumed last word lines will sooner or later will all die. So in SSD, even though one block has a huge amount of data, and one page becomes, actually one word line becomes unreliable, we define whole block is dead. And extending this idea to the SSD level. For example, in SSD, if you have a, we call bad block, something cannot store data anymore reliably. And if you have one or two, typically one bad block occurs, we assume rest of block will sooner or later all will unreliable. So that's the end of SSD lifetime. So you may think we may use a smaller SSD for quite a long time, but the underlying assumption was one block becomes bad, sooner or later, all the rest of blocks will become bad and you lose data. So that's why the industry set the one block, and when the one block of SSD becomes dead, SSD becomes dead. It's the end of lifetime. Okay. So in this case, from this idea, in this case, what you can see is who decides lifetime of this block is this worst word line. So in SSD, because reliability is very important, data reliability is very important, design is more or less based on worst case. But as you all know, if we want to optimize, design should be support common case. So worst case based approach and common case approach, there is a big gap. So my second presentation, putting those gap small scale, and then you want to extend worst word line to live longer. Okay. So here, if we look at each word line's lifetime, and so there is when this happens, so this worst word line becomes dead, we are losing this amount of potential data write or storage capacity. Okay. So this is a huge waste. So we want to do something in this direction. So how to utilize this wasted potential of strong word lines. Okay. And then we also look at who is responsible for flashware. And we knew erasure operation is the key, but we validated in 3D. In 3D flash memory, erasure operation takes even higher portion on flashware. So we knew from this test, this is a 2D. So from this data, you can consider we have to do something on eraser side to word line to live longer. Okay. So when we erase word line, actually when you erase block, and then we do some damage on the flash cell, and the key is how to reduce those damage somehow. So whole idea, whole direction we are trying to show in guided erase approaches, we want to make, for example, this worst word line. Okay, it dies after 6.5K erase cycle, and we want to make this word line longer, live longer. So main strategy is we erase this word line when is appropriate. We erase this word line with low stress erase mode. So we designed low stress erase mode. So we apply low stress erase mode to this W word line. And because even though erase was applied, it was with low stress and it can live longer. So we extend the weak word line's lifetime longer. So this weak word line is still live, and we try to utilize this unused strong word lines capacity. This is the main idea. Okay, so let me show you how to do it. Okay. So we call this approach guarded erase because we do erase, but some word line we do with the low stress erase, and we call that as guarded erase. Okay, so let me show you the key ideas again, summarize. So we have 10 word lines, and here I assume word line 0 is the weakest word line. Okay. So this word line we write erase once, twice, and word line 0 will become unusable up to 10 erase. And unusable means when you write this word line, we may not meet the ECC's correction capabilities. But it becomes, for example, ECC can recover 50 bits every 1 kilobyte. And when we write word line 0 after 10 erase, it may produce like 60, 70 bits errors. So it cannot be recoverable. Okay, so here you can see many potentials are wasted. So instead of this way, we introduce low erase mode. Okay. So low stress erase mode we introduce, and whenever we find that some word lines are getting older too fast, we give that word line some rest. So we erase with the low stress mode. So in this picture, for example, after 2 erase, we find out word line 0 is ahead of all others already. So next time when you erase word line 0, we erase word line 0 with low stress erase mode with this white box. So introducing this way, so here you can see smaller white box than blue one. So it means word line 0 is less damaged. Then it erases regularly. So intermixing with low stress erase mode, appropriate fashion, and what we can do is we can do, in this example, we can do 12p cycles instead of 10p cycles. The lifetime increased. Also, if you roughly look at this picture, we write more data to our SSD. But here, when we do low stress erase mode, there is some side effect, a serious side effect. So when I teach fresh memory to my computer science students, it's almost impossible to talk about voltage and threshold. So I give analogy of using paper and erase. So low stress mode, erase mode, you erase very soft eraser. So your paper can live longer. Yeah. So that means when you erase, data are still there, not cleanly erased. So you cannot write data there anymore. So when you, for example, in word line 0, when you erase with the low stress mode, what happens is you cannot store data there until you erase word line 0 is normal erase mode. So your capacity is reduced. When the block capacity is reduced, what will happen in terms of SSDs? Now you have a smaller space to write. When you have smaller space to write, what happens is your write is amplified, more object collections, and your performance is dropped. So there is a trade-off of using low stress mode. You have to risk some low performance, also lower capacity. So what we did was we developed some intelligent way of managing WAP, write amplification factor damage versus lifetime increase. And so all these things are managed by FTL. Okay, so that's the key idea of this approach. So any question on this proposal? Yeah.
So I'm not actually fully aware of low stress mode arrays. So does it still keep some electrons in the charge trap, or? So
you write data to the word line, and then you erase whole block.
Yeah.
Then you can write another data to the same word line. That's a normal erase mode.
Exactly.
But low stress erase mode. So physically speaking, what happens is you apply some high voltage.
To remove all the electrons.
Yeah, you remove all the electrons out of the cells. Yeah. And here, low stress mode, we apply low voltage when you erase that particular word line. So some garbages are still there. So when you program, you are not sure which state you are in. So you cannot store data anymore. So in some sense, for example, I don't know here you have that kind of system. But in Korea, we have a survey system. Some seats are reserved for older people or pregnant women. So only unless you're a pregnant woman or older people, you are not supposed to sit there. So the goal is to make older people live longer. So that kind of special treatment. So this weak word line 0 is weak. We give this weak word line some rest. by applying low voltage.
So when we apply a low voltage, still, so we cannot remove all the electrons from the charge trap, right?
So until the next erase, we are not using the voltage line.
I understand, but can't we basically verify the voltage threshold in that basically volt line, and then depending on what we want to write,
It becomes too difficult, too complicated. Yeah?
Okay.
Yeah, so you have to assume this state will now particular volt line 0, it will be 1, and other volt line. So I think it's doable, but doesn't make sense. Yeah. Okay.
I have a question. How did you manage to get that granularity of arrays for each word line? Because from my understanding, the substrate is shared across all the word lines, and that is how we do the block arrays. So
yeah, I will show you. So I conceptually I want to answer any questions, but details are following. Yeah. So you have to support low stress erase mode. That is the hardware changes, and then this reduced capacity directly affects performance, and you have to manage it software-wise. This is done by FTM. Okay. So low stress erase mode is relatively simple. Okay. So this picture, depending on your background, I don't want to really go deep, but so when you erase, and each word line we apply 0 voltage, and then we apply very high erase voltage. So all electrons are removed from the cell. But when we do low stress erase mode, what we do is for example, we want to erase word line 47 with the low stress mode, and we apply, for example, 3 volt to its gate voltage instead of 0. So stress is proportional to the difference between V erase voltage minus this gate voltage. So now you have less 3 voltage, stress is reduced. It's just amount is small, but actually it makes difference. This is how we support the word line wise low erase mode. Yeah. So block is erased as before, whole block is erased at the same time, but depending on weak word line. So we identify weak word line in advance. Okay. So we know which word lines are weak, and then those weak word lines, as FTL decide when we apply low erase mode or when we apply regular erase mode, depending on your workload. Because when you apply low stress erase mode, your capacity is reduced, and then garbage collection may happen very frequently, and then it drops whole performance. If that happens, you are not supposed to use erase mode because it doesn't make sense to extend drive time with the poor performance. So that is done by FTM.
Sorry.
Oh, yeah.
Yeah, I have one more question. So in the lowest stress erase mode, if we wait for a longer time, can we make sure that the cell is completely erased, or
just waiting?
Yeah, so basically when we increase the duration of that pulse, can we make sure that it's completely erased that word line, or?
So you mean apply low erase mode for longer time?
Exactly.
Then you will have the same effect.
Oh, I see. Then we have
I haven't done, but it might be. But
okay.
Then erase time will increase.
Yeah, erase time
significantly.
For sure. I agree. But does that have the same reliability issue?
That I can answer. You need experiments. Yeah. But certainly there is trade-off. Yeah. You can consider. Yeah. Okay. So with this as a main mechanism to control weak word line, and actually we created something called guarded erase mode, 9 guarded erase mode. And this is a little detailed, but let me give you some high-level insight here. So there is a 9 different erase mode. Reason why we created a different guarded erase mode is each mode you can select how many weak word lines you are going to use. Okay, so guided erase mode 1, we only apply 8 weak word lines when you apply the low stress mode. But mode 9, we apply 36 word lines. So 36 word lines making weak, and then what happens is you will have capacity-wise big drop, and in performance-wise, it may have a big impact. Okay, so we combine number of weak word lines, and then how often we use this mode. So by combining this one as a main mechanism to control weak word line, FTL will use this one to optimize it. So our optimization goal is actually not the lifetime only, but actually total amount of data written to the SSD. We want to maximize this one. So if you look at the SSD, physical capacity is given, and then maximum P cycles are given, and then write application factor is given. This is the simple formula which can tell how many host data was actually written to the SSD to the end of SSD lifetime. So you want to maximize this one, but if we use guided erase, what happens is we can increase maximum P cycles because we extending lifetime of weak word lines. However, what we losing is we lose physical capacity, and physical capacity is reduced. It increases write amplification factor. So these three parameters interact each other, and it's the FTL's responsibility how to manage all three by choosing which guided mode when, and then we maximize this terabyte written matrix or total amount of data written actually. Okay, so we built FTL, and this FTL decide weak word line detector, which was already set, and then we choose which mode to use, and then we monitor performance. In this case, we monitor WAP changes. When WAP is increasing very quickly, we are not going to use erase mode much. And if we aggressively apply guided erase mode and WAP is still manageable, and then we are keep using. So the kind of extra modules added, and we used NQSIM-E, based on NQSIM actually from your group. And so for this work, what we did was we actually extended NQSIM and we call NQSIM-E. Here E stands for enterprise. And actually we wrote short paper on this one. And one of the problems we found NQSIM as produced here is it's very useful simulator, but in terms of enterprise applications, there are several weaknesses because when SSD manufacturer typically employ like enterprise sensitive optimizations, and those optimizations are not included in NQSIM. So that's why we extended NQSIM to NQSIM-E. And one of the key extension of NQSIM-E over NQSIM is actually garbage collections. And most of modern enterprise SSD, when you do garbage collection, you don't do one block at a time. You do erase, before you erase, you copy small portion of pages. So then you write, and then you reclaim small number of pages. So you work on much smaller granularity. So we kind of added it into NQSIM, and so we made NQSIM-E. And we tried this 8 workload, and this is the result. So total, in terms of total amount of written data, and we can, on average, we can improve about 21%. Yeah. So if you can see the first 3, we can improve lifetime 29%, and project 2, we can improve only 11%. Baseline was, okay, I didn't explain here. BPM is, so you may consider because now that there is a serious process variability within single block. So you may think a logical solution is, instead of bad block management, you can use bad page management. Okay? So you find some word lines are not usable anymore. You can just exclude those pages out of that particular block. So we use that bad page management. So 2.1 means up to 2.1% of total capacity can be regarded as bad page. And 5.2% can be considered as a bad page. Okay. We compare this one and we have about 21% gain over bad page management is 9 to 30% gain over baseline page regularity here. And so let me point to one interesting point here, because there are big changes in efficiency in 29% and 11%. And this difference comes mainly from warp impact. Okay, so for example, project 2, when we erase particular word line is a low stress mode, so making particular word line is weak word line, and it will reduce block capacity, and then that reduction in write block capacity affect performance very seriously. So in project 2, you should not reduce capacity aggressively. So all we did was we can reduce small number of word lines, and then we erase those small number of word lines by low stress mode. On the other hand, this is a 29% efficiency version. We can apply many word lines as weak word line. So by making more word lines weak word line, we can extend drive time more. Okay. Okay, that's there's not much performance over it. That's fine. Okay, this is the second part. Any question on second part?
A couple of questions.
Yeah.
On YouTube. Yes, it's a bit late. So basically, we are the question is to that that we are making erase operations. The damage caused by the erase operations evenly spread out across all the word lines.
Some sense, yeah.
That is the first question. The second question is, how do you determine which word lines to apply guarded erase to? And are those word lines the closest to the threshold?
Okay, the first question is actually, we are not spreading out the damage. We are making some room for weak word lines only. Okay? Because we apply only low stress mode to the weak word line only, not the strong word line, we don't care. And we predetermine which word lines are weakest and which word line is second weakest based on characterization. And within block, and it's a similar pattern, depending on where you locate it, the best, worst, and second worst, we can characterize it. And based on that information, we apply word line, the weak word line ideas. Yeah. Okay. Okay, no question?
So I have a question also, like, did you characterize like how many like weak erases do you need in order to amount for a normal erase? Like to have the same equivalent wear?
I didn't follow your question. Can you repeat?
Yes. So I'm saying, like, I'm trying to picture, like, you say you have two types of erases, no? Like a weak one and the normal one.
Yeah, right.
So I'm trying to understand, like, how many weak erases do you need to amount for the same wear as
okay. So we are not trying to use multiple weak word lines to make one normal word line. So we only apply weak or normal at the same time, depending on which word line. For example, here, let me show you an example. So in this example, so here, so when we erase this block third time, we select word line 0, which is weak word line. We apply low stress erase mode, and all other word lines except the word line 9. This is also identified as weak word line. And all other word lines we erase with normal erase mode. So
Yeah.
we do at the same time.
Yeah,
And
but
after,
my question is more like, did you quantify like how much, like if we see like you have an increase in bit error rate values, right? Every time that you do an erase. So if I compare the increase in bit error rate values of a normal erase.
Oh, okay. In quantitative way, okay. How much
Yeah.
I am not sure if you have that information in the paper or not, but
It's about like 2 times, 3 times, 10 times.
yeah, about twice, I would
Twice.
say. Yeah. Mhm.
And then a background
Okay,
question.
quite significant, yeah.
Background question related to that. So like, does the erase harm, no? The increase in bit error rate values depend on what do you have stored in the cells, or it is independent on
So
this?
let me further explain that on your first question. So actually, this one, okay. So we apply here 3 volt here. Whether 47 when you apply low stress mode, if you can apply higher voltage here, it will give you low stress erase mode. And we haven't tried because we cannot implement that one. So if you can apply higher voltage into gate voltage, you have a lower stress. Okay, so that we haven't explored.
Yeah, but my question is like, instead of like, so if there would be a difference in the erase damage, no, depending on the content of the value of the word length, could you just avoid writing? So you erase once, and then in the next cycle, you don't write anymore to this word length.
Yeah, for low stress erase mode, yeah, we don't use.
And then I erase like normal over time. So does
Yeah.
it have an effect also, that kind of mode, and then you don't need to change the hardware, or it doesn't?
No, it doesn't. Next time when you erase regular, we just change into 0 volt instead of, so we can select this one.
Yes, but the harm of the erase operation doesn't depend on the content of the cells.
Contents of cell, and that I don't
What
understand.
you have stored there, like what is the voltage that it's stored in each of the NAND cells?
So up to low stress erase mode or regular normal erase mode.
Normal erase mode.
Normal erase mode, it goes back to normal, so you can store anything. As with other word lines, no restriction.
Okay.
Okay.
Good.
Okay, let me go to last topic. So I think what time is it? Okay, last one is I'll summarize quickly this one. So actually, this is ongoing work too. So last one is not characterization based. This one is based on our observation. Okay. So here we propose processing in storage kind of work, but we look at if we moving compute into not inside SSD, but inside the flash chip. So that's the key motivations. Okay. We call processing in flash this technique. And so our main motivation was when we go up 3D flash memory in vertical direction, and people tried was actually now it's in commercial product too, is in order to sense cells like a voltage level and also sending out data to outside the chip, and there are peripheral circuits it takes about 20% of cell area, and in order to increase this per die density, people moved this peri under the cell. So this architecture they call cell over peri or peri under cell, and different names depending on which company, but main idea is putting peri into under the cells. Okay. So in this structure, when proposed, we observed unless current design at that time, a few years ago, doesn't change, there are significant amount of free space on bottom. So instead of putting this one, so currently there are many different proposals in here, but we look at, can you put some computing element here? So instead of in storage processing, is it feasible to do in flash processing? That is main idea. So for example, this one from the literature of different vendors, and according to flash cell array and versus all the peripherals, and we can assume about 78% of this bottom die area is available for some computing. Okay, so this is processing in flash idea. Motivation is, if you look at the processing in storage in SSD, it's very promising and interesting. But here you put the computing element in the SSD controller or at the similar level. And if you look at process in this way, what I observed was the problem is, as SSD capacity increase, and typically SSD capacity increase by putting more flash chips and using parallelism. And then this acceleration capability is not scalable in some sense. Because if you have more data in your SSD and you want to accelerate, you want a higher acceleration capability. Also, with more flash chips and data transfer becomes a bottleneck. Because here, right-hand side graph shows as increased number of chips per channel shows data transfer from chip to the accelerator becomes bottleneck. So in order to solve this problem, we thought putting accelerator inside SSD, or accelerator inside flash chip instead of inside SSD controller will solve these two bottlenecks. You don't need transfer data, and also accelerator is in every chip, it becomes scalable. Acceleration capability becomes scalable. Okay, so this we call processing in flash, and then this acceleration function we call X-core. So this flash application we call cell level X, so we call it CUX. So this is cell level X flash chip. Advantage is when you do accelerate, controller requests each chip to compute some function FB in this case. Then inside the flash chip, you read data and then compute, and only data needed for further processing will pass to the SSD level accelerator. So this, at the same time, it solves data transfer overhead is reduced, and also parallelism increased because acceleration is all distributed in flash chips. Okay. So what are the changes? One of the key challenges actually, it becomes very difficult to read reliably inside flash chip because, as you know, SSD, there is a SSD ECC encoder and decoder at the SSD control level. When you read sense data and then move to here and then you recover or potential bit errors, then transfer to host. So here, it's not possible because now you cannot recover bit errors without using this one. So key challenge is how we can reliably read inside the flash sheet without putting very heavy ECC encoder here. That was actually our key challenges designing this one. And second challenge was, if you're putting computing here, it consumes power. Okay, so our initial goal was putting some DNN accelerator inside flash chip. Okay, and it very quickly became it's impossible. No power to do that. Okay, and so one thing we learned was, as soon as you put some computing inside the flash chip, okay, whether it's a DNN or any simple filtering operation, what becomes key concern is power consumption increase very, very quickly, because if you look at the flash memory is a very slow device. And power management is relatively easy. But now you have to do computing inside and many chips at the same time do some heavy computation. Power can be a real concern. Okay. So with these challenges, let me show you, we have done, this is actually ongoing work, but we have done simple evaluation using pattern matcher as an example. So a typical case where this kind of acceleration is useful is you have a simple operation which doesn't depending on the previous operations result. So it should be data dependent and high parallelism. So in this pattern matcher, for example, we have some log, and we want to search particular keyword out of this each log stored in Birdstyle. And then this kind of operation, they are all independent, not data dependent. There is no data dependency. And this is useful for this kind of application. To build this pattern matcher, and we developed two new commands: pattern initialize, and then read out command only when the pattern meet our particular the fresh read meet matching patterns. So let me show you how we support these functions. Okay, so again, the key challenge is reliable in-flash read. So without using off-chip strong ECC engine, we want to recover data inside the flash chip with a weak ECC engine. So at the current version, we solve this problem using LDPC. So if you are familiar with the LDPC ECC algorithm, actually LDPC support two modes of decoding: hard decoding and soft decoding. Okay. And currently we support a very weak version of hard decoding inside chip. And we felt it can be doable. And then at the same time, off chip, we have a strong, complex LDPC decoder engines. So LDPC is very nice in flash read, in the sense we encode once, and then depending on which decode, you can decode multiple times. In our case, we read and then we do weak on-chip ECC, and cells are pretty reliable state and not much errors. Okay. Then on-chip ECC will work. And when on-chip ECC cannot recover, then so correction fails, we send into the off-chip engine. So you kind of two-mode ECC decoding. So obviously the performance improvement of this PIP pattern matcher depending on how often you have to go out to decode data. Okay. So that's one challenge we solved, and then you actually implemented some pipeline the patient. So this shows examples, because you have to pipeline processing with the data sensing, and so more operation going on. So obviously this will help performance, but it will increase the power. So this becomes a big challenge. But we currently implement it this way. So we compared processing in storage with our processing in storage combined with the processing in flash, and using two workload, grab and SQL query TPCH. And if I summarize the result, compared to baseline, using only processing in storage, acceleration in storage, we can achieve almost 10 times speed up here. And also in terms of power, I mentioned you there's a problem, but in terms of energy consumption, because computation is done much efficiently without moving unnecessary data out flash chip to the SS controller, SS accelerator, energy efficiency is also improved almost 10 times. So it has I think it has a strong potential, but At current technology, putting very strong computing engine into flash chip doesn't make sense. And we are looking into actually putting very small predict kind of engine so that we can improve read retry problems. So we are working on, so as a kind of side product of this one, actually went to the read retry optimization as key extensions. Okay, any question on processing in flash? Okay, so let me summarize my talk. So in the beginning, I mentioned I'm working on most of logical layers, including NAND flash to the host. And this is some of our current work. And so in terms of reliability, we are working on read distort management as a key topic. And because this is very important problems in modern large capacity 3D flash memory. And then performance optimization, we are working on read retry, and also I'm working on small random read optimization as a key project. And lifetime also we are working on, and then special function. I mentioned to you we are working on ransomware protection inside SSD, and this is very, I don't know, personally it's an interesting problem, but it's very difficult because there are so many hacking attempts and exploiting different aspects, and it's very difficult to do everything inside SSD. But we are working on using something called program context and combining with the SSD internal protection, and we'll see. We are actually writing papers right now. And also, last topic is low power flash, and this is a new topic, and we haven't explored much, but I think it's getting important because host interface is getting fast and fast, and channel bandwidth is getting fast, and then it will affect power consumption, because the only way you can meet high bandwidth host requirement is parallelism, because we cannot make fast flash. So we have to more IO requests processed at the same time, then power budget becomes issues. So we are looking at and this low power aspect of flash and SSD as also this is a topic. Okay, thanks for your attention, and I hope it helps some of your understanding on flash memory as well as SSD. Thank you. Any question? Yeah, I'm open to question. Any questions? Okay. Yeah. Okay. Thank you.
So thanks a lot for everyone attending today's Safari Live seminar, and see you in the next.
Okay.